Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this morning we're delighted to have Alexandra Kola from University of California in Berkeley telling us about merging techniques for combinatorial optimization.
Hi. So I had a story to say, which I am going to say since it's relevant. So 4 days ago, I left my bag in the car, and my car got broken into, and my laptop got stolen. And I lost all my work, which I hadn't backed up. So I had to redo my talk basically from a really old version that I emailed my advisor. And the moral of the story is that you should leave everything for the last day, because then everything can be done in a day, right? So we'll see how it goes. And also back up. Always back up. Okay. So that's me, and I'm from Berkeley. I'm going to be talking about two areas that are very heavily worked on in theory and outside theory, spectral graph theory and semi-definite programming, and how these two areas are connected, basically, in more ways than one. So, sorry, question. Do I have a roller for the slides, or just with the... Didn't say that. No, that's fine. No. Okay, so spectral graph theory is basically studies the eigenvalues and eigenvectors of graphs. And the relation between spectra and expansion introduced spectral techniques as a very popular tool for applications in a lot of areas. For example, image segmentation uses spectral techniques, and basically the use of spectral techniques in revolutionized image segmentation. Eigenvalues and eigenvectors of random walk matrices led to PageRank algorithm, and constant degree expanders have been a very useful and popular tool in coding, communication, and theory in general. Also, eigenvalue methods in convex optimization have been used long back, as far back as Lova's theta function, bounding chromatic number of graph partitioning, graph labeling, routing in networks, and a lot of other unlisted applications. And now semi-definite programming is basically an optimization, a convex optimization problem, optimizes over the cone of positive semi-definite matrices. And it has been a major tool in fields like automating control systems, signal processing, communication networks, circuits, statistics, finance, and a long list. And in theory, in particular, it has been used heavily to create approximation algorithms for NP-hard problems mostly. And basically, sometimes it works great, sometimes it doesn't. And the study of semi-definite programs in theory, see here for MaxCat, the semi-definite program, which I'm going to get back to, is very interesting by itself. So we have these two very popular areas. And basically, if you look at them closer, then you see that they're connected in more ways than one. So in particular, semi-definite programming, the constraints of semi-definite programs take the form of linear matrix inequalities, and they use eigenvalue bounds. And on the other hand, most eigenvalue optimization problems can be cast into an SDP. So in my work, basically what I do is I try to merge those two things to create approximation algorithms for combinatorial optimization problems, and examine limitations of SDPs when they cannot create good approximation algorithms for NP-hard problems. And all these references to my work is what I'm going to be talking about, some more, some less. But let's see an example of what I've been talking about so far. So what is this duality between spectra and SDP? The max-cut problem, which everybody probably knows, it's find the max-cut in a graph. And it's a maximization problem. It can be cast as a quadratic integer programming formulation, with xi is +1 for one side of the cut, -1 for the other side of the cut. So is that clear why that's the max cut problem?
Yes, but maybe specify what The W's are...
It's the weights on the edge. So it's a weighted max cut problem. I'm just giving a very intuitive slide of why these two things can be connected. I'm not going to talk about max cut at all after that. So, yeah. OK, so however, integer programming, it's NP hard. So you cannot actually solve max cut. Yeah. And then the next best thing, or maybe the next best thing is an STP relaxation of max cut, which Gemmons-Willison came up in 95 and relaxed the condition that these things are vectors and not plus minus 1 values. You have an STP relaxation of max cut. But let's see what happens if we look at the dual. So we look at the dual, and it turns out that the dual gives an eigenvalue bound on the value of max cut. And actually, this lambda mean that it's basically a bound on the dual value, and therefore, by strong duality, the bound of the primal value. It's the most negative eigenvalue of the graph that we're looking at. So it turns out that you start with an SDP. By STP duality, you come up with an eigenvalue. And these two things give basically an idea of why these STP and spectral are very well connected. So let's see now. In particular, in my work, I'm interested in expander graphs. So in expander graphs, through STPs and through their spectra.
Excuse me. So for that particular application, you could do that directly too, right? You don't need to go through
The
STP.
max cut?
For the eigenvalue map. Yeah.
Oh, sure. No, of course. I'm just giving an example of how I'm not going to talk about max cut. You can do it directly. You can do it with STP. I'm just giving an example of how an eigenvalue of a graph is connected to an STP. Of how through duality you come up with why do you study spectra? Why would one think that max cut, it would be useful to look at spectra, for example, and not something else?
Well, I think the point you're saying that the connection between spectra and cuts is older than the connection between SDP and cuts. So I guess from one perspective...
That is very true, of course.
From one perspective,
but
the connection of spectra to cuts is not a surprise.
No, I'm not. But in the next second part of my talk, I'm going to be showing a similar STP duality thing that from an STP gets an eigenvalue, and I want to indicate that. That's why I'm introducing it through max cut. I just thought it was a simpler example to look at. I didn't want to imply that that's the only way to do it.
The point perhaps is that some STPs and spectra are duals of each other. Is that the point?
That is the point by a very more broad definition of duality. So it's not the only point. It's one of the points. I gave a practice talk, and somebody asked me to give an example of what I mean by duality, and that's why I have this slide there. So I'm sorry if maybe I shouldn't have given a practice talk. But anyway, that happened after my laptop got stolen, so it's actually one of the things that can be done in a day. Bear with me. OK, so I'm particularly interested in expander graphs. And let's look at why and what, basically. So in computer science, there are major goals to create fault-tolerant networks, fix connectivity problems, speed up software testing, cluster in social networks, and everything. So what did I do? Oh. So for example, you have a network, and you're required that if this highway here fails, then you have other ways to go. So that's a fault-tolerant network. And for all those problems, the major component, a common denominator that actually facilitates the solution of those problems, is an expander graph. So that's the expander, not the girl. So yeah, expanders are graph with large conductance, fast mixing time, and we'll see more. So edge expansion. Well, an expander graph has large edge expansion. Edge expansion is just the ratio, the minimum of the ratio of edges that cross a cut over the number of nodes in the sparsest, the smallest side of the cut. And if a lot of applications actually look for balanced and sparse cuts, like the ones I mentioned before, image segmentation, divide and conquer heuristics, and other stuff. So it would be great if we could find a sparse cut. It would be amazing. But we can't, because it's NP hard to compute. So the next best thing is to find a reasonable approximation for that. And what is a reasonable approximation for that? Well, its algebraic connectivity. Just a quick review, like graph Laplacian is this matrix that has the diagonal, in the diagonal the degree of its node minus the adjacency matrix of the graph. And algebraic connectivity is basically the second smallest eigenvalue of the Laplacian. And it's polynomial-time computable, so that's great. But why would I look at that? Well, there is Chigger's or Alon-Milman inequality. I don't know how you want to reference it, but let's say Chigger's inequality for now. It gives a reasonably good approximation of expansion within a quadratic factor in the worst case. And also it relates to mixing rate of Markov chains and other nice properties of graph. So there you go. It's a very good, most of the time, a very good, not most of the time, a lot of the times, it's a very good approximation for the sparse cut. And sometimes during this talk, I'm going to be going back and forth lambda 2 of the Laplacian and lambda 2 of adjacency matrix, which are sort of related. So if you have any confusion about which lambda I'm talking about, just please ask. But I'm going to try to be.
Why do you say it's a good approximation for the sparsest cut? Is an approximation for the isoperimetric or expansion ratio?
I'm not saying that it's always a good approximation
But
for
where's the cut?
the ratio h, the one I defined before.
That's the ratio.
Quality of the cut.
Yeah.
I'm saying the sparsity of the cut I defined here in the
Right.
previous
I thought you
slide.
wanted to find the cut, though.
I'm not sure what you're
I thought you
asking.
wanted to find the sparsest cut, and you wanted to approximate finding the sparsest cut.
I'm approximating the cut. So if there is the lambda 2 gives a bound of how big the cut can be. So it's not that you can find the sparsest cut always, like by looking at eigenvalues, it's not that you can say, okay, maybe if I'm quadratic factor apart, it's in the worst case, it's really bad. Like it's not a good tool. But a lot of the cases when it's not, maybe these things are closer together, that's just a bound. Then you can actually find what is the lower bound of the sparse cut.
The sparsity, right, I think the confusion is, you're not finding the cut, where the cut is geometrically in the graph, you're finding the
Oh, yeah. I'm just saying, what is that graph behaving like? I mean, in particular, the eigenvector cuts, like if you do spectral partitioning with the eigenvectors, then you can find cuts that behave with that guarantee. But I didn't say that. I don't know if that's your question. Okay.
Wouldn't the cut be just the eigenvector corresponding to lambda 2? The sign of that, right?
I mean, yeah.
So you have
a threshold function, and you can basically find it by randomized. It's not necessarily plus minus because it could be shifted. But yeah, I mean, again, that's not my point. I mean, I'm just trying to show why lambda 2 is important. Okay, so lambda 2 is important. Great, we all agree. Okay, and I'll be talking about this. So I'm going to give you how the talk is going to be structured. I'm basically going to look at expander graphs through semi-definite programming and going back and forth between spectra and expansion. So the first part, I'm going to be talking about recent work on creating cost-effective expanding networks via local sparsifiers, which I'm going to define. Second part, I'm going to talk about the Unique Games Conjecture, which is false on expander constraint graphs. And third part, which is just going to be like a slide with 2 of my papers that I've done explaining about lower bounds for SDPs. If I have time, but maybe not. So, creating cost-effective expanding networks with the use of local sparsifiers. Let's see what does that mean. So, by the way, this algorithm, we have a patent with Microsoft. So we have a patent with Microsoft. This algorithm, I'm just saying. So the problem is augmenting a graph with a few good edges. So you're given a parameter k, and you're asked to find k edges from a set of candidate edges to maximize its algebraic connectivity. So we have this graph, and then optimal solution has these orange edges there. And say this gives maximal algebraic connectivity. In general, that's an NP-hard problem. And no provable approximation algorithm was known before our work. There are a lot of heuristics done, but nothing with a guarantee. So a special case, which I'm going to be talking now in this talk, is that if the graph actually could be made into an expander with k edges, then find them. So I'm going to give a constant approximation algorithm for that problem.
So again, algebraic, could you remind us what algebraic connectivity
Oh, is it second lambda 2 of the Laplacian?
So you want to get you want to increase the gap.
Optimize lambda 2 of the Laplacian by adding k edges.
Maximize the connectivity means to get a largest possible spectral gap.
Yes. So yeah, I mean, you could see it either way. But so the point being that, I wanted to introduce algebraic connectivity and see why I care about this problem and not edge expansion. Like, why don't I look about edge expansion and I look at algebraic connectivity? And that problem deals with that optimization quantity of the graph. So you look optimizing algebraic connectivity. And in particular, if the graph, like if this optimal solution here was an expander graph, and we're guaranteed that the graph could be made to an expander, I'm going to show you how to basically do it with maybe 10 k edges, not k edges, but so it's a by criteria optimization. And so the interesting case is like when k is not root n necessarily, but around there, because if it was n, I mean, you could put an expander. If it was constant, you could just brute force and find everything. So you need something in between. Okay, so that's an eigenvalue optimization problem, as we said before, and it has an SDP relaxation. So we have an SDP. We're at the SDP, but the optimum is a weighted graph. It could be the complete weighted graph with total weight k. Instead of k exact edges, I have total weight k. And I might be unfortunate enough to have like the complete graph, and I don't know how to pick k edges out of those. So we need a way to round the SDP and find k edges. So now SDP rounding has been like long back a very crucial problem, very important problem that people worked on, and Gemans-Williamson had the random hyperplane rounding. Many other problems use that. Then ARV introduced a new technique for rounding, and actually what we do, we have yet another new technique for rounding, which is called local sparsifiers for that particular problem. And what that does is we find order of k edges and approximate the best lambda 2 or algebraic connectivity within some constant. So
It's on the lambda 2 or on the k?
both. So we have by criteria optimization. So a quick review for whoever doesn't know what a graph sparsifier is, just one slide review. We are asked to approximate any graph G by a sparse graph H. So we have our graph G, and we want like a sparser graph H with like weights on edges that somehow approximate G. And the notion of approximation we use is basically that these two quadratic forms are very close to each other, or that basically eigenvalues are the same. The whole spectrum are the same.
So who has BK there?
Oh, sorry, yeah. That's Ben-Zur-Karger with Kat sparsifiers, Spillman-Tang, Srivastava, Spillman, and Batson. Sorry, yeah, I'm really bad at reading the references. So basically, we're asked to find a graph that approximates, for all practical purposes, the spectrum of G.
Not all practical. Some practical.
For some practical purposes, true.
So the spectrum.
And the spectrum is approximated within 1 plus or minus epsilon by this definition. But I mean, that doesn't make much sense so far. Why would we look at that? Well, this is actually a generalization of Kat sparsifiers for Ben-Zur and Karger paper, like long back. And if we relax that requirement and ask that H approximate the original graph only for cut vectors, just for every cut, the weight that goes across the cut is preserved, meaning that you just restrict that requirement to 0, 1 characteristic vectors of the cut, just because this is the total weight of the cut, then you can see somehow how this idea comes from. And in fact, the last paper, Batson, Srivastava, and Spillman, proved that every graph has a sparsifier with a linear number of edges. Or if you see deeper in what that says, it says whatever eigenspace I want to approximate, I can find the order of that dimension number of edges to approximate it. And for example, example, scaled constant degree expander, which is not an expander here, but I just could not draw an expander, gives a sparsifier of the complete graph. So if you scale everything by n over d, then you have basically the whole spectrum of complete graph is same as whole spectrum of scaled expander. Okay, great. So that's a graph sparsifier.
What do you mean by scaled? Expander?
by n over d. So
What?
because you need to preserve the total number of weights, you need to scale every edge by n over d. So say it's a d-regular degree expander. So in order to a complete graph has eigenvalues and order of n.
The edges.
Yeah.
Okay.
So in particular, you just need, instead of all the edges that cross the cut to have the same weight, you just need the total weight to be preserved. So what is a local sparsifier, though, and what do we do? So as we said before, we're looking for an integer solution. But the SDP could be the complete weighted graph. So that's our SDP. And if we could try to sparsify a la Batson, Srivastava, and Spillman, I'm going to call it BSS from now because it's too long to say, we could get up to order of n edges, which is not good enough for k squared n. Well, this is really bad. Exactly. So that's really bad. So we come up with the notion of local sparsifiers. So by the way, I'm again really horrible. I didn't mention that this is joint work with Sankwa Tang, Yuri Makaritsev, and Amin Saberi from when I was in Microsoft New England. Yeah, I'm sorry about that. So we introduced a notion of local sparsifiers, and the idea is to relax the sparsification requirement and only ask that the sparsifier is good on a specific subspace. So, if we relax that requirement for this x's in some subspace of dimension k, then by a modification of the proof, we get linear number of edges in the dimension of the subspace and find order of k edges that approximate my graph in the sense that I want. That is very good. And now we remember that the problem was if the graph can be made the expander, then find the k edges. So what subspace do we look at, though? Because there are so many choices of k-dimensional subspaces. It's unclear what you should look at. So if my original graph plus the optimum number of edges was an expander, which means that the lambda 2 of the resulting graph was some constant, and by looking at the min-max theorem for eigenvalues, it says that basically by adding k edges, the best you can do is lambda k in increasing order. You cannot do more. And in particular, if k was bigger than n, you would look at the rank of the Laplacian you were adding, of the Laplacian of the new edges. And if you say that just the SDP is a relaxation of the original problem, then basically, if you restrict of the eigenspace of the first case eigenvectors of Laplacian of G, you get a good graph with constant algebraic connectivity. So the approximation that we get depends on lambda k and lambda SDP. So if both of them were constant, if one of them are constant, then we're good. In particular, if the graph can be made to an expander, one of them would be constant. However, there is a catch. That works great for expanders, but that's not our general theorem, which I'm not going to present right now, but I need to say that what happens if lambda k or lambda SDP are horrible, like are 1 over root n, I don't know, or 1 over n. Well, then we have a more general theorem that also has a different notion of sparsification. Yeah, exactly. So what happens if they're horrible? Okay. I already said that. I should have shown. I'm sorry. So then we also have a general theorem that actually sparsifies for the whole subspace, but observes the following: that we already have G. So G is already a really bad sparsifier, maybe, for G plus optimum, G plus SDP graph. So maybe it's a really bad sparsifier, but at some directions, it's going to be good. Like if you look at the largest eigenspace, then it's going to be good. You don't need to do anything. So by using that intuition and a lot of technical work, which I'm not going to talk about, we get the generalization of that sparsification requirement with few extra edges. That works well in a bigger class of graphs. And that's the people I've worked with on that, which is... Yeah.
You won't tell us which graphs, so even to define...
Oh yeah, it works for graphs that lambda k is, for example, of order k over n. And we are currently working on the whole spectrum, but that's work in progress, so I don't want to. So that's the first part of my talk. If you have any questions about that, that's a good time to ask.
So maybe you can say a few general words on what makes a sparsifier local as opposed to global. So
local is something I named it. It's
that's why I'm asking.
Global sparsifier basically. So this work the general theorem. It's not a local sparsifier, it's a global sparsifier in the sense it approximates every direction. So before, like the previous slide, when we restricted to that subspace of first k eigenvectors, I call it local because you look at the restricted subspace.
But what you get in the end is an expander, so why is it?
No, the sparsifier is, you basically want to choose k edges out of however many edges the SDP has. So I'm not referring...
Those edges, I mean, so you're saying the sparsifier condition isn't holding for all vectors?
It might be, but I'm not requiring it. Yeah.
So in this situation, when you get an expander, which directions you can...
Well, when you get an expander, nothing matters because everything is within constant. So in that case, I mean, it really bear with me. I just named it local by myself. You know, it's not, I just wanted a name for it. And it's not local in the sense of locality that you might have in mind. I just didn't know how to name it, basically. I mean, I have all these crazy names in that paper that...
I don't think he cares about the name. He just wants to understand the
Oh, no,
properties of that you're
it's just the only locality is that you only look at that subspace, you project everything onto that subspace, and you work as if your Laplacian was a rank K matrix on that subspace. However, the other, I mean, the next slide is more global, and it actually does not project onto anything. It just proves that there is a way around it.
So the more general notion of local sparsifier is actually not local.
It's not local, yes. Remind me to change that. I call those star sparsifiers, and the reason being because when we were working on it, we had the star on the board, on the property we wanted, and we always would call it star. So I have a whole paper with a theorem that says star sparsification. Not kidding, a whole paper, only with the name of star. So I didn't want to come and say, okay, we have the star sparsification, so I put local sparsification. Yeah, anyway. So now I'm going to be talking about unique games and how the unique games conjecture is false on expanded constraint graphs. Well, I mean, nobody conjectured it for expanded constraint graphs. I'm just going to show that unique games is easy on expanded constraint graphs. You can solve unique games. But let's go back for a step and say basically what is going on with NP-hard problems. So NP-hard problems are hard to solve. But the next best thing is approximation algorithms. So for example, there are a lot of important problems like click, max reset, set cover that have almost optimal. They have an approximation algorithm that, and actually it's proved that basically that's the best you can do up to some lower order terms sometimes. So this is pretty much tied using the PCP theorem and the parallel partition theorem. And you know, there's not too much more to do in approximation. However, there are these other important problems like vertex cover, max cut, max KCSP, that there are these sometimes folklore, sometimes SDP based, sometimes I'm not sure how this works, SDP also. Algorithms that actually the NP hardness that has been proved for them has a large gap, like is not matching the approximation algorithm guarantee. Are those problems still open? That we're going to see in a bit. And there are other problems like the sparses cut that basically we have a squared log n approximation algorithm due to ARV and no hardness other than like no pitas basically is known. So this is still open. So let's see. In approximability in the lens of Unique Games Conjecture. So now we wanted to have all these, the vertex cover and the max cut and max KCSP problems, and we wanted to find a way to close the gap either way. Like, is it better approximation algorithms or better in approximability lower bounds? Or better, I mean, by some definition of better. So let's see the previous board or table that we had there. We have these gaps here. And if you assume something that's called the Unique Games Conjecture, basically these gaps close. And I mean, for the non-uniform version, this becomes better. For the uniform version, there's nothing else known, again, unless the original Unique Games graph has some expansion. That's just the motivation. I haven't defined the Unique Games. I haven't defined the graph. So let's see what is Unique Games. a special case of it, which is the easiest case to deal with, linear equations mod k. So you're given a bunch of constraints that have the form xi minus j, so equals some value mod k, where k is the alphabet size, it's a prime. And you're asked to find the maximum number of constraints that can be simultaneously satisfied. So it's a maximization problem. And you can see it as a constraint graph. So you have, for each variable, a big node. And then its edge represents, one of these constraints between the variables. So that's the Unique Games constraint graph, the underlying graph that I'm going to be talking about. But you could also see it as some other graph, which is called the label extended graph. And its variable now, its original variable is replaced by 3 little variables that correspond to the labels. Here we have label size 3. And its original edge is replaced by edges between the corresponding labels that satisfy the constraint. The reason why it's called Unique Games and not just games is because this thing is a matching. It's a permutation. So its constraint just is a one-to-one matching function. And that's called the label extended graph. Are we clear so far? I'm going to be using this tool a lot, so we need to understand. Okay. So we had like this graph, and that's clear why that's the unique game, or the game.
Well, I don't see what game is here, but I see...
Okay, the games comes from a different motivation, which is prove or verify games. I don't want to get into that, but forget the games, yeah. So this is just a modeling of what I'm saying. Find the maximum number of edges that can be colored or satisfied. But you can see it as, here we have 3 labels, white, silver, and gray. White, silver, gray, so it's 1 to 3, 1 to 3. And here we had before the identity permutation, so white goes to white, silver goes to silver, gray goes to gray. So the way to satisfy that original edge was to assign either white, white, either silver, silver, or gray, gray. That could be an assignment that would satisfy that constraint. So it's just a different model of the unique game, which it's like a lift. In graph theory, I'm pretty sure you know that these are called lifts, but so in particular, this lift can be used as a modeling of the unique game. And basically now the nice thing about that is that you can visualize the labelings by picking out, if you assign white, white, white and white, then this is not a completely satisfying labeling, and you can see why from that picture.
But the thing is, the problem of what you have to find in this new setting is a little bit strange, right? You have to find...
Well, you don't have to find anything so far. I'm using this as a tool to find what I need to find. But if you can bear with me for a couple of slides, you might have a better understanding of why I'm modeling it like that.
Okay, but just the problem that corresponds to satisfy the maximum number of constraints in the original question is something a bit more complicated, right? I mean, you have to find at most one edge on each.
Sure, but I'm going to be talking about that a lot. So just if you still have questions after that, please let me know. Okay, so in particular, as I said before, these 3 edges are satisfied here, and this is not. And the optimum value of the game is 3 over 4. I mean, that's just a picture of how you can relate satisfying assignments and stuff, okay? So that are unique games. And what is the conjecture? Basically, it says that this unique game problem is hard to approximate, and it's due to Cobb, 2002. Right? In other words, it says that for large alphabet sizes, it'd be hard to tell that if the game is 99% satisfiable or 1% satisfiable. Well, that's great, because as we saw before, it leads to all this tightness in approximation and approximability results. So, however, nobody, could say, why is it true or is it false? What's going on? It's a notorious open problem that nobody knows what to do. There have been approximation algorithms, though, for unique games. And these are some of them. And as you see, all the first 5 depend on n, or the alphabet size. Sorry, that should have been k. I had it p for a prime, but this is k. So either depend on k or on n, so asymptotically it could be really bad. And what we prove in that paper, which is joint work with Aurora, Tulsiani, Kott, Starrer, and Vishnoi, and it's a merge of 2 papers, basically. That's why we have so many people. We basically have an algorithm that does not depend on K or N. It depends on expansion. And it basically finds a 99% satisfying assignment if the game is 1 minus epsilon satisfiable and the graph is a spectral expander. So, we have a different kind of dependency here with the rest, which works very well on expanders. And that's what I'm going to be talking about in the rest of the talk. But let's sit back and say, why one would even look at expanders. Why would, not look at planar graphs, I don't know, something else. Well, there is this expansion and sparse-scat things I've been talking about, and also our previous table that said that sparse-scat is a very weird problem. Nobody knows how to prove in approximability results for that. So there is unlikely, even assuming the unique games, that there is a reduction from unique games to sparse-scat. Not true, just unlikely. The reason being that if you start with a unique games instance that does have a sparse cut, then all known reductions, or long code reductions, say, that have been used in approximability, they're going to create a sparse cut instance that also has a sparse cut. And that is not going to depend on whether or not the unique games instance is a yes or no instance to begin with. So there's no way with these current techniques that we have to do this, to create such a good reduction. Unless the unique games has some expansion, which also was observed by Kott and Vishnoi, 2 of my co-authors, in a manuscript. So there is actually a reduction from an expanding unique games instance to sparse-scat. And the reason being that situation here cannot happen if the graph isn't expanding. So the only good cuts in the sparse-scat instance would correspond somehow to good labelings. So there was this off-the-record belief that expanded graphs were indeed maybe not the hardest instances, but hard instances. So there was this belief going on. When I was talking to people while I was working on that problem, they were surprised that I thought it was easy on expanders, actually. So that's the picture. And now what we show basically is, as I said before, that when the game of unique game is a yes instance, a 1 minus epsilon satisfiable instance, then, and the algebraic connectivity of the graph is large, then we have a good algorithm that recovers a 99% satisfying assignment.
Yeah, I'm going to protest about that title, because if you say unique games conjecture is false in some case, it means in particular that it's false. But
okay, so
these games are easy on expanders, right?
I explained before, yeah. So
before.
I should have changed that. You're right. But I said that it's not false on expander. Yeah. Okay. So why? Let's see. Because before I said that expanders were believed to be hard. What happened so far? Well, for intuition, let's look at a perfectly satisfiable game. In a perfectly satisfiable game, it's easy to determine if a unique game instance is 100% satisfiable. And let's look at that weird graph and pretend that this was an expander, because it's not. But pretend that this is an expander. As we observe, this is a perfectly satisfiable game. Here you can pick gray, white, and silver. Gray, silver, anyway, you can pick, it has exactly 3 perfect labelings. And if the graph was an expander, a cut that corresponds to the original graph would cut a lot of edges, because it would correspond to the expander cut, which would be large. And in particular, the only good cuts that cut exactly 0 edges are those that if you pick out the correct labels for its node. So that's why this is a nice picture of the unique game, because you can see in that cut sense. So you see that if you pick out a satisfying labeling, put it in one side, and the rest on the other side, you cut 0 edges. So this instance of linear equations have actually 3 perfect satisfying assignments, and it's disconnected. It's 3 copies of the graph disconnected. Okay, so that's a very nice picture, but we already know that perfectly satisfiable games are easy to determine. Well, and the 1 minus epsilon game is an almost perfectly satisfiable one. So I'm gonna talk about what that means, but intuitively one would expect that now we're in good shape. We could do something about it. Okay, but then I was talking about all these SDPs and eigenvalues, and sparse cuts are hard to determine. So even I just said sparses cut is an NP-hard problem. What do we do? Like, how can you find a cut that corresponds to a good labeling or something? There's no way. Well, let's go back to my max cut slide, which probably should or shouldn't have been there, but we'll see. And let's look at what now we can do. So remember, max cut, I showed you a reduction, not a reduction, a duality between SDP value and eigenvalue. And what happens in unique games? Well, it is a combinatorial optimization problem. It can be cast as an SDP. And in particular, what happens if you look at the dual? Well, let's see what happens if we look at the dual. It turns out that we again have an eigenvalue bound. So dual objective is bounded by some lambda 2. But what is that lambda 2? Well, remember the label extended graph that before you were asking me? Well, it's a lambda 2 of that graph. So the adjacency matrix of that graph is just the original adjacency matrix replaced, and its entry that was 1 would correspond to an edge. It's replaced by the permutation that's sitting on that edge. So now we have a great tool. We have SDP duality gives you a lambda 2 bound of that nice matrix, which is the matrix of the label extended graph. So now let's go back to the previous slide. And we look at the game again. So we had all these cuts that correspond to expander. They were big. The other cuts were good that correspond to labelings. How do we relate cuts with spectra? The only eigenvalues of the matrix M that I was saying before, the adjacency matrix of the label extended graph that are large, are the ones that correspond again to perfect labelings. And all the other eigenvalues for expanders are comparable to the lambda 2 of the original constraint graph for the expansion. So basically, this lambda 2, as well as the rest that correspond to assignments, are large for expanders only if and only if the game is satisfiable and for however many satisfying assignment it has. So now we're in good shape. We have a tool. And let's do some reverse engineering, because I promised before that we looked at perfect games and then something magic happens and we have 1 minus epsilon games. Well, let's start with a 1 minus epsilon game. This edge here is a problematic edge. It's not satisfiable. But we can, what did I do? Sorry. But we can think of it as coming from a perfect game that some bad adversary chose an edge or epsilon fraction of the edges and adversarially perturbed those edges to make them bad. So that's now my original game that was a perturbation of the other game, or vice versa. We look again at that matrix that I talked about before, and we observe that, as I said before, there are as many large eigenvectors that correspond to large eigenvalues, as many as satisfying assignments. And these are actually a basis for those is the characteristic vectors of the labelings of the assignments. So each block has a 1 unit and the zeros otherwise, 1 corresponding to the flag that lights up for white, gray, or silver. And that's like the eigenspace. Well, that's supposed to be the eigenspace. And for expanders, what we prove in that paper, that all other eigenvectors have really small eigenvalue. And now let's see what that means. Look again at the 1 minus epsilon game. That game can be seen as now, in a matrix sense, as an epsilon perturbation of that matrix that was here, but now it's not anymore, which should have been. It's an epsilon perturbation of the matrix, and it's an epsilon perturbation of that eigenspace. Well, that doesn't say anything, only that the fact that we prove for expanders implies that in the perturbed sense, the assignment eigenspace has a large gap from the rest. So there is label k dimension of large good eigenspace, and k plus 1 and more, they're just really bad eigenvalues. So there is a big spectral gap. And perturbation of matrices tells us that when that happens, this perturbation does not change things by much in the spectral sense. So eigenvectors in the right-hand side space are close to eigenvectors in the left-hand side space. And in particular, what does that mean? Well, it means that for every vector here, you can find the vector here that are close in L2 norm. And remember what were the vectors here, though. These vectors were satisfying assignments. These vectors were characteristic vectors of satisfying assignments. So in particular, you could somehow, with one more extra step, find those vectors. And let's see what's the extra step. So we have a labeling algorithm. Compute the first k eigenvectors of the perturbed game. a discretizer span. So basically, after that, since K is about log n in the application that we're looking at, this has polynomial in many number of points. And basically, as I said before, there is a vector in this epsilon net that is close to an assignment vector. And what does close mean? Well, it basically means that this vector here is going to have most blocks with a single big entry, and some blocks really bad. But these blocks with a single big entry would be the big entry that corresponds to the correct labeling. So we just have that vector to us, and there you go. That's a 99% satisfying assignment. So in particular, I want to say one more thing, because we have two proofs of that theorem. I mean, the previous proof works for linear equations mod P. This works for general case. There's yet another connection with spectra and SDP, which can be greatly demonstrated in that proof, which I'm not going to talk about. And it's in the paper if you, Anyway, so basically now in the other proof, what it does, it's again yet another novel rounding of the SDP solution for the unique games, the SDP that I showed you before. And you basically have a vector solution and for unique games, and you create a vector solution for the sparsest cut SDP without triangle inequalities. And if the expansion is big, constant, note that basically if you have local correlations between edges, that means that SDP value aligns vectors for edges, then it somehow would mean that it aligns globally vectors, because in expanders, however much you walk in edges, you walk in a random pair of vertices, which I need like another half hour to explain. That's why I'm not going to explain. Okay, so that's basically the end of the unique games part of my talk. And if you want to ask any questions, you should now. Okay, this is just one slide about a couple of other things that I have done. One of them is with Lee, and we have a construction of integrality gap for sparsest cut, uniform sparsest cut, that matches Kotvich-Noy hardness and gives some intuition and probably some way around proving tighter bounds, which I'm going to probably send to CCC. And this we have, I don't know, for those of you who know SDP hierarchies, we were looking at Lasserre hierarchy for a while. It turns out it's harder than we hoped it would be, but we do have one additional round gap. We developed a whole new technique, basically, to get one additional round gap for vertex cover 2 minus epsilon. That's with Sachi and Kalle, and we're sending that to CCC as well, I suppose. And now, if you don't have any more questions, I'd like to talk about what I want to work in the future and what I've been working on.
Well, we'll have 6 hours of questions later.
Yeah, no, I mean, yeah. So I've already been thinking about some very exciting problems that relate to my work mostly, and I want to share them with you. So one of them is resolve the Unique Games Conjecture using spectral techniques, because we know that SDPs fail. We have bounds. Kotvich-Noy showed SDP cannot do more than that. And I wonder, since there is another way around it, can we use that to solve unique games on graphs that SDP fails? Nobody knows. I've worked on it with people in spectral graph theory, with Joel Friedman, an expert on expanders and stuff, but we couldn't. For a day, I thought I solved unique games, but then I realized that I haven't, so that was disappointing. Then, uniform sparsest cut, as I said before, I really want to work on that problem more, and see if I can use the techniques we developed in that paper with Lee, and close the gap. Basically, I believe there is a lower bound of squared log n that matches the RV. And maybe we're going to have to use heavier free analysis. We're thinking about entropy conjecture and stuff like that in the past, but we still don't know how to put all these things together. And investigate the power of these notorious SDP hierarchies, which basically very, very few lower bounds are known, and very, very few algorithms are known. So either way, I'm going to be very happy to say, well, these strong, powerful, seemingly SDPs can give you better algorithms or not. Those are some things I've been thinking about, and then some exciting problems I plan to think about. which I didn't have time yet. So that came as a natural consequence of our work in sparsifiers. And the question is the following. Give me a graph and describe it with the effective resistance map. For those of you who don't know, I can explain one-to-one. But I can describe with the effective resistance map. Is that enough to specify the whole spectrum? Is that like a one-to-one function, say? Or what is the property of the graph that can be revealed by that map? Then I'm interested in random behavior, like random graphs behavior on SDPs, in hierarchies and not hierarchies and whatever else has. I've been looking on the clique problem for last year. It turns out it's much harder than we thought so as well. I mean, we have some half-finished work in that, but I don't think I even want to, start digging into that right now. And then something that you've all suggested in the past, which I have been, telling myself to work on, but then I've been busy with all this other stuff. The ternary recursive majority function, and using techniques from additive combinatorics a la Tau to get an intuition for random matrices, basically, like little Wood-Alford problems and stuff like that. I tried to work on that a couple of years back, but turns out that these two people are better than me. That's a joke. But yeah, I would like to explore techniques from additive combinatorics in random matrices and see what intuition can I get from that.
Other questions for Alexandra? Okay, we will contemplate and ask you more later. So, thanks again.
Okay.